Good morning, folks. Here we are at COMP1720/6720 for the very last time this semester, too, in 2022. It is week 12. I'm sure everyone has a lot of stuff going on. Stress is probably the correct emotion. If you're not stressed about your assessments, can you give me some of that? I'm not sure how to deal with big assessments and marking at the end of the semester. It's always tricky. If you're joining me live, I think there are a couple of people joining me live, maybe. Let's see if I can get my... Oh, well, it's gone somewhere. I think there are a few folks joining me live. If you are joining me live, thank you so much for being here. Chuck your comments over in the team. I should open up Teams somewhere so I can see the comments. If you aren't joining me live and you're watching later on Echo 360 or YouTube, you're very welcome too. I'm very pleased to have you as well. And if you're not watching it, then I won't greet you because you're not watching it, I guess. This is sort of some kind of paradox about people not watching lectures. This is the last week. We're talking about another one of our recent development-y topics. And the vibe today is to talk about creative machine learning. Creative machine learning. What is that? How can we use it in P5? What kind of art have people been making with machine learning? Connected to the kind of interactive art that we've been making in this course, I guess. And one of the wild things, I guess one of the wild things about machine learning is how much this has become one of the most talked about fields in computing and one of the most talked about ways of doing computer-based art in the last few years. And some of that discussion makes a lot of sense, and some of it is related to a hype cycle, hyping things up that maybe aren't as impressive as they're hyped up to be. Things we're not going to talk about today include, generating large numbers of images for no reason, because when you're making art, we like to make things for a reason. We like to make things interactive in this course. We like to do things that are coherent and relevant and refer to a theme or make sense in the world. We're not making images for no reason. If you're making images for no reason, it's not really art. It sort of has to have some element in it which makes it stand apart. So we're talking about uses of machine learning in a creative way where we care about the data, where we care about the outcome, and where we try to make it interactive with the viewer. So I've got some examples to show you later. We've got some code to look at in this lecture, and it should be a bit of fun. So this is usually a fun one. So if you're here watching me live, I hope you can shout some things at me in the chat or something so I know what's going on. Time for the finishing touches. Last admin corner for the semester. Your major projects are due on Monday at 9 p.m. in the evening. We are still looking forward to any discussions on the forum. There's a few questions that I've been answering still. There's questions that are not quite answered yet, and I have to get to the answer before we'll be able to close off those ideas. If anyone's got any questions about anything to do with the major projects, please ask it on the forum. Please don't email me because sometimes I miss my emails. Asking on the forum is the best way because I go through the forum posts regularly in a sort of with a COMP1720 hat on, so I know what I'm doing when I'm looking at that. There's still lots of time for developing your major project in lots of different ways. If you've got a big idea that you've already started, maybe it's not not hugely sensible to change it completely at this stage, but you can still guide the direction. If you haven't really started yet, you've got a bunch of little ideas. Try to find the best of those little ideas and start to pad in some extra stuff around it. Remember that all of the projects in COMP1720 are about quality, not quantity. We're looking for something which is going to look nice on a big screen, engage someone when they walk by it, and hold their attention for a couple of minutes as they interact with it in basically a positive way. So we don't need to have a 2-hour game, that's way too long. We don't need to have something which has 12 scenes because then you wouldn't have time really to understand and get the impact of all of those things in that experience. We do need to have something which is an actual artwork that sits on the wall. So when it's sitting on the wall and not being interacted with, it should have a sense of trying to engage the viewer, have some kind of hook or speak to the viewer in some way. All of these things that we've been going through over the last 12 weeks, it's your turn to incorporate them all into your major project as best you can. And the main thing about the major project is that it should be something that you care about. It's your major project, not mine. We're giving you an opportunity in this class to do a project where it's much more open-ended than you might see in other computing courses. So you get to have your own choice about what kind of a artwork you're going to do. Is it representational? Is it abstract? Is it something else? What kind of interactions you're tracing? How you want the viewer to feel? How you express the theme to the viewer, and how you want the viewer to understand that theme in your artwork. All of these questions are for you to answer, not for me. So we give you a very simple theme after hours, and it's your turn to do a lot of the thinking and caring about this project in order to get something that you can then think back on and think hopefully positively about. And if you ask your tutors this week in your lab, go to your lab and ask your tutor, what did you do for your major project? Hopefully they're positive about it. Some of them might feel a bit like, oh, I really wanted to get something else done and I didn't have time. All of your tutors did great major projects, so they probably didn't need to add that extra piece there. And maybe with a bit of perspective now, they can say, oh, I wanted to add this really complicated thing, but I couldn't because I didn't have time. And it turned out that I was able to refine my other stuff to make a better project anyway. So hopefully that's the discussion you can have with them. But talk to other people about their major projects, people who've done this course. Try to sound out what kind of a thing what feeling you might like to have about it at the end of the course. Avery's there in the chat, cringing a bit about their major. So, sorry, Avery. Definitely, definitely. Sometimes there's cringe. Sometimes there's happiness. I'm not sure if the distance of time adds more, but it's certainly a moment in time, and you get a significant chance to test your mettle in terms of creating something from scratch. So this week's topic, creative machine learning with ML5.js. So we're doing a bit of machine learning. We're not taking this in the same way that you might in any other machine learning course in computing, because we're only going to use this for making interactive art with P5. So we'll go through a few things. What is machine learning? In case you've never heard of this term before, many folks here will be first-year computing students. Maybe you've studied a little bit, you've heard about machine learning, you don't know a lot. You might not be a computing student, you might have never heard about this in your life, and you might think, that's too hard for me. So I'm here to say it's not too hard for you to use machine learning in art if you want to. Second question, how can I use machine learning in P5? And third question, how can we make art with it? Same questions we've been asking about everything this semester, really. So what is machine learning anyway? What is machine learning anyway? A few things. First definition, creating computer programs without explicitly programming them. So normally when we teach computer science, we teach you to think, I've got a problem I need a computer to solve, and I'm going to break that problem down into a number of steps, and then I'm going to use a programming language to instruct the computer to do each of those very simple steps carefully. So if you want to draw a picture, we break the picture into shapes. We set the color, choose the shape, choose the location we want that shape to be, draw it, and then do that for every shape. So we're breaking down a problem into very simple parts. The idea of machine learning is that we say, okay, there's a problem we want the computer to solve. We're going to define that problem, and then we're going to get the computer to write its own program to solve the problem, without us having to do the programming part. So we set up some kind of way for a computer to write its own program, do these steps, and then measure how well it went against those steps, and use the results to teach it to do it better. And so the learning part is the computer getting better at writing its own program to solve a problem. That's the learning part. Just like humans learn when we want to do something, or kids learn. Kids learn to speak by trying to speak badly, don't they? My daughter is 2 years old and she speaks all the time and says a lot of words that sound wrong, and I have to learn how to interpret the word she's saying, and I repeat it back to her, and she says it again, I repeat it back, and then the next day she says it a bit better because she's got that process of reinforcement from feedback. So the same idea with machine learning, getting a computer to solve a problem, create its own program. There's some kind of feedback about whether that worked or didn't work, and the problem is solved better next time. A simpler way of putting it, one aspect of machine learning is algorithms, that is programs, that learn by example. So this is one approach to this, is that you show the computer the solution to the problem. Like you say, here's the outcome I want, and here's how to solve it. And it learns that, and then you say, here's a different outcome, here's how to solve that problem. Learn that, and you learn many examples, and eventually you can generalize over your examples. That's one kind of machine learning. There's other kinds. Here's another one, algorithms that learn through experience. This is more like how kids learn basic skills. They try something, have a bad result, try it again, slightly better, try it again, slightly better, and then they're getting better over time through experience. Another thing about machine learning is it's kind of a big deal with $3 signs. A lot of people expect that certain kinds of machine learning could make them money in various ways, and so there's a lot of investment and excitement about how to do machine learning better. Of course, it's fun when you get a computer to do something that you haven't exactly programmed it to do. You feel like you're a super programmer. I'm just programming the computers to program themselves. So that's an exciting field to be working in, and certainly there are people currently making lots of money in various ways by applying some things that are sometimes machine learning. There are other people who are applying things that they expect to make a lot of money, and so they're putting a lot of investment into it. And there are people who have already invested a lot and not made a lot of money, and maybe learning that it wasn't all that they'd hoped for. So there can be lots of ways of approaching this. Money is a complicating factor in research and art, so it certainly makes things a bit tricky to understand sometimes. Machine learning kind of problematic, and 3 exclamation marks. And we'll talk a little bit more about that later. I don't want to go into great detail about machine learning and ethics in this lecture. It's not the topic here, but we should be thinking, whenever we're using a machine learning system, where that came from and what the data was and what the outcomes could be, what that result could be. So we need to understand our systems that we're applying, and that means having a bit of context about how they work. And you'll see later that when we get something complicated and just download it off the internet and apply it, sometimes it can have some results that we don't expect. So we can think about a few of the problems with relation to artworks. Again, not going into great detail about the potential problems of AI, and not trying to critique it in a hugely strong way. Just saying, just with everything else, when we download something off the internet, we need to understand context when we're applying it. So let's do some machine learning. Let's do some no-code machine learning. Suppose the boss wants a program where the screen color changes to red when the mouse moves to a certain location. So far so good. We've got a mouse X location, that's the left-right location of the mouse. When mouse X is 15, that means very far left, there should be not a red background. Mouse X is 75, there should not be a red background. Mouse X is 173, there should not be a red background. 250, there should be a red background. 312, there should be a red background. 375, there should be a red background. So this is for a very small screen, it's just 400 pixels wide. So we want this program to satisfy these conditions. The boss has given us a specification. Or the boss has given us, in some sense, the expected solutions, and wants us to create the program to do this. So how would you do it? Well, let's write an algorithm which is configurable. So we've got this algorithm here, a very basic algorithm. If mouse X is greater than some number, then we make the background red, and else make the background black. So what's the configuration part about this algorithm? The configuration part is the question marks, because we can put any number we want there. So this algorithm we could use to solve many problems for many bosses, as long as that problem involves making the background red. But if the boss gives us different information, we could configure it in a different way. So what would be a good number to use For this background, well, the background seems to change to red somewhere between 173 and 250. So if we put our cutoff for the background changing to red at maybe 200, that should satisfy the problem. I think I've got an example here somewhere. Oh, here it is. So I'll put in 200, make my sketch, I move my mouse across and it turns to red. So far so good. Very simple configurable algorithm. If the boss gave me different information and wanted everything above 100 to turn red, I can reconfigure this algorithm again. So far, we've only had one decision to make here. And that decision was, is it going to be a red background or a black background? And we only had one number as input, which is the X location of the mouse. So it's a very simple problem to solve. And in fact, we don't need any complicated machine learning algorithms. We can just look at the data, the expected solution, and from that data say, oh, it's got to be somewhere between 173 and 250. And if the boss had given us a lot more data, we would still be able to just look at it. Maybe you could order all the data by X location and work out where you want that cutoff to be. One decision, one input, very simple problem. So what if we had more inputs? Maybe we could make, in that case, more complicated decisions because we'd have more data to look at. And the problem with more inputs is it quickly becomes unmanageable for us to just put it all in a spreadsheet, for example, and just try to figure out where the decision should go. If you've got mouse X and mouse Y and you're trying to make one corner red, well, that's probably doable. But if you've got like 50 sensors and they've all got different numbers coming in and you're trying to make some decisions, more complicated decisions, choose between 10 options rather than one option, then it's going to be hard for us just by eye to look at the data and make those decisions. So it's better if we use a computer to look at that data in some way and try to distill all that down into a decision that's going to work. It's likely to get more complicated to do this configuration, which is why we need to do this process with a computer. So let's just stop for a second and turn back to our art making processes. So we would often use pictures and visuals in art. And if we have a picture, we could use that as an input. And in fact, as you know, a picture is just a big array, or a 2D array really, of pixels. So this pixel's green, this pixel's brown, this pixel's white, this pixel's pink. So a 2D array of pixels in X and Y locations. So if the picture is 100 by 100, then we've got 10,000 different pixels to look at. Pictures are 2D arrays of colors represented as numbers, just like we already know that. You know how to represent colors as numbers already. If we had enough ifs and elses, maybe we could make something that could make a decision about a picture. For instance, we could have an algorithm that decides whether a picture contains a dog or not. It would be a doggo classifier. If this picture is a dog picture, it classifies it as true, and if it's not, it classifies it as false. So a trick we use in machine learning to make configurable algorithms, or the trick is that we do this design for a configurable algorithm that can take a lot of numbers as input and just have one number as output. And this is a lot of neural network or a lot of machine learning systems in the last five or 10 years are based on this idea, taking a lot of numbers as inputs, boiling it all down to one number as an output. So the configuration step here is choosing how much of each input to listen to in making a decision. So you might have some, in the previous example with the mouse, we had a cutoff that we'd chosen to say this should be red or black. And in this case, we're taking a lot of information from different inputs and deciding or weighting them in a certain way to decide which one is contributing more to that final decision, that cutoff decision. So one example of this kind of design is a a very simple algorithm called a perceptron, which actually is not from the last 10 years. It's from the last 60 years. So it's 64 years old, the perceptron idea. It comes from 1958. So you can read about perceptrons more. The idea is you take a lot of inputs just as numbers, you multiply them by another number, which is your weight, then you add up all of those numbers, and then you kind of squish them down into a number between 0 and 1 in some way. So you're taking a lot of numbers, squishing them down, and using that output to help make your decision. It's a very simple bit of maths, but it can be useful in this kind of decision-making configurable algorithm scenario. So fast forward 50 years, what have we learned? Or 64 years, in fact. What have we learned in 64 years about perceptrons? 3 tricks that are really important about machine learning and perceptrons. One is that if you feed the output of perceptrons into other perceptrons in a kind of network, like in this picture, some perceptrons go forward into this one goes forward to this one. Each of these second layer of perceptrons has a number of inputs as well, and their one single output is being copied to 3 in the next layer. So we can feed the outputs of perceptrons into more perceptrons to make this little network. We can make better algorithms to choose the configuration. So even though we've got the same perceptrons, we might be using different algorithms to take our data and update the configuration over time. The bit that does the learning step is a process that we call optimization in machine learning. So optimization is tricky. There are lots of different algorithms to choose from and people working on new ones that work even better. And the third trick is if we have much bigger and much faster computers and we have a lot of data to learn from, the whole thing works a lot better. And that's the trick which is really hit in the last 10 years, is having really, really fast computers that are really accessible. So a lot of people can have them, and you have one in front of you. They can get a lot of data from the internet, sharing data in different ways to train these algorithms, to learn these systems, learn these configurations, and make them work a lot better. And this thing over here, it's called a network of perceptrons. Another word for it is a neural network, which is this typical a feed-forward neural network. It's a very common and popular machine learning algorithm in the recent times. So this is this other name for a perceptron, an artificial neuron. So, some terminology here. What have I just said? This terminology is important because we need to use it in talking about some code in the next few slides. So the terminology here is that a model in machine learning is an instance of one of these trainable, configurable algorithms. A pre-trained model is a trainable algorithm which has already been trained, so we don't have to do the training process, the learning process. Training/optimizing is using data to teach a model or have the model learn how to work better. So we've got a model that's untrained, we get some data and an optimization algorithm, and we put that all together to make a trained model. Prediction or inference is when we've got a trained model and we then use that to solve a problem. So we use it, give it some new data that it hasn't been trained on, and generate an output. And then classification is a name for a machine learning task where we're looking at some data and choosing what it represents from a range of options. So all the different options could be called classes, and we're giving it one class, one label from this range of classes. So an ML task for choosing a class or description for a piece of data. And you might be thinking, if you're a computer science student, where's all the maths? Where's all the maths? Well, if you want to make the learning process go faster or make new kinds of models no one's ever seen before, it's a great idea to have a maths or a computer science major. But if your main goal is to make interesting art with the most relevant new technology of today, well, you're ready to go. You've learned what you need to know from 1720 by learning about how people interact with computers, by learning about the different aspects of art, by learning how context matters in what you create. You're ready to go. You don't need to do any more maths to start making art with machine learning. So here's the bit of how to do this in Java in P5. So P5 by itself doesn't have machine learning features, but there's another JavaScript library that has a similar name to P5 called ML5.js. It's a similar JavaScript library that provides some machine learning models that are trained, models that are not trained in a web browser and hooks into P5. So it's very convenient to use ML5 to add some machine learning stuff to P5. This lets you load up pre-trained models and you can start doing some prediction in different contexts right away. So it's related to P5.js. It's not the same thing. It has a different website, ml5js.org. It's related to and inspired by P5. Just have a look at this website. No justice, no peace. Friendly machine learning for the web. And there's lots of cool stuff here. A big community of people trying things out. And it's really interesting to try. Oops, where's my task gone? Okay. Let's do some. First thing we need to do for ML5.js is to load the library itself into our index file, our index.html file. And if you're in a P5 web editor sketch, you can just copy this line here, which loads up the library into the index.html file. I think I've got one right here already. I'll just make that my next tab so I don't lose it. You can see your index.html file here. You've got one of these in all of your assignments in your major project as well. So if you have a look in there, you could see that there's the script line to load P5. There's a script line here to load p5.sound. And then in this example, I've added a line of code to load up ML5.js. Then, when you're in your sketch, you can already access the ML5.js functions and features. What do we do next? Oops, no. So I need to load another one. So let's do what we were hinting at before. We're going to do a doggo classifier. So we'll use a pre-trained model called MobileNet, which already exists within, I've got a problem here. Oh no, my mouse needs to be on the other screen. No, it's not. This is going to be interesting. Come on, mouse. Okay, got that. I'll have to take a little break in a minute to sort out my mouse problem. We're going to do the doggo classifier. So we need to do a few things. We've got to load up a classifier. We're using this MobileNet classifier. This is already built into ML5. It's pre-trained and ready to go. And then we classify an image. So I'm just going to copy this into my code. We're just going to do this in setup. I might do it in preload actually. We load up classifiers in preload. And right now we don't have an image to classify yet, but we'll do that in a minute. And where does the output go? This is one of the things about ML5 is that it's set up so that it doesn't interrupt your draw loop basically. And one of the ways that you could interrupt your draw loop is by taking a long time to classify an image. So doing machine learning predictions is one of these things which can take a little bit of time on a computer. It's a complicated operation. So if you had this in your draw loop, it could slow down your frame rate. So you don't want to do it in your draw loop. We use a different approach, which is to have a what's called a callback function. In this case, we're calling it getResult. And the callback function is going to receive the results from ML5 and then do something with it. So we're going to have to make our getResult function somewhere else. Make that over here. Function getResult. Okay, and we can do something with our results here. Oh, I see. I'm on the wrong side. Oops. That's potentially annoying, but I'll get used to it. I've got two laptops for this lecture, and I don't know if you ever have two Apple MacBooks next to each other and you're logged into both, your mouse just starts working across both. I don't quite know how that works, but it can be a bit confusing when it happens the first time, or the millionth time, as is happening to me. Okay, so how are we going to do this? We need to load up an image. This is not so hard because I've got a going to have my classifier, going to just classifier, just declare that variable, and I'm going to have an image. And my image, I've actually already got an image loaded up into this sketch, doggo.jpg. So doggo.jpg is going to be here. Image equals load image assets doggo.jpg. There we go. Okay, so I've got my image, I've got my classifier. It's going to do the classification and then it's going to print out the results. But it's going to be pretty boring if we don't even show what the image is. So I might just display the image in our sketch so that you can see what it is. Image 00. This image is from Unsplash, by the way, so I'm definitely playing by the major project rules. So there's my doggo, and it's probably loading P5 ML5JS and doing the classification, and here's the result. So we've got our output is an array of 3 objects, and each of these objects is a possible description of our image. So MobileNet is this version of MobileNet is a neural network for classifying images from one of many titles. I think there's 1,000 classes in the MobileNet training set, and we can see that it thinks that this doggo is in fact a fountain, and it has 90% accuracy, or 9% accuracy actually. 9% confidence in that. It thinks that it might be a jigsaw puzzle, 7% confidence, and maybe a park bench, only 3% confidence for the park bench. So overall, not great. This is definitely a doggo and not a jigsaw puzzle or a fountain. We can just add a little bit more code to do something with the prediction. I might just print it on the screen. Let prediction equal nothing yet, and we're going to put that prediction in there. Text prediction, like down the bottom somewhere. 10,500 or something. I'm just trying to write some text on the screen. Nothing yet, that seems fine. And then when we get our prediction, we will say that its prediction equals results 0.label. So when our prediction appears, it will change to fountain. So this doggo, that doggo is not a fountain, definitely not. So what are we going to do? We can classify video as well. I'm not going to classify video right now. I might get some other, I think I've got some other options. Yeah, I do. I've got some other options for this doggo classifier. ImageNet labels. Here's one I prepared earlier with a couple of different doggos. That one's a fountain. So I'm going to instead change it to doggo 2, a different doggo here. We'll see what doggo 2 does. So that doggo, it knows what it is, Labrador Retriever. That seems more realistic, doesn't it? Let's just have a look at the prediction options here. Labrador Retriever, 28% confidence. Golden Retriever, St. Bernard's. Well, it's not St. Bernard, but it seems like a Labrador or a Golden Retriever. I'm not really an expert in dog classifying either, so I'm going to take their word for it. Window screen. Window screen doesn't really seem likely. What have we got here? Window screen, 18%. Window shades, 6%. Shoji, 5%. So this one's completely wrong. what are we learning here? Well, these systems are not perfect. Machine learning is not perfect. MobileNet is one of these pre-trained algorithms that happens to come with ML5. It might be useful for some things. Let's see if we can find something else that's useful for. We might be able to use it for, rather than an image, to just look at what I'm doing and classify that. So I'm going to, instead of that, start using, what did I do? Click to link. Rather than looking at the image, I'm just going to have it look at video using a webcam and try to get it to classify that instead. So I'm actually going to change to my other screen where I've got this example done. I'm using another screen because I don't want to mess up my webcam while I'm streaming. So let's have a look at this. Oops. Let's have a look at my second laptop. I'm still here, but I'm looking over there. So in this example, rather than loading up an image, I've got a video which is going to create an image capture from my webcam. Fit.hide, do the same thing, load up the MobileNet classifier. I'm going to create canvas, start my classification with got results, and instead of just doing it once, it's going to have to do it regularly. So it's going to classify. The classifier is already connected to the video. So ML5 image classifier, you can add a video as an argument, the thing that it's going to get its classification data from. So we just need to classify that and give it the callback function. In the callback function, we basically do the same thing, prediction equals result 0.label, and then we classify again. So it's going to just classify as fast as it can the frames that are going by in that video. Whatever frame it happens to be up to when it makes the previous prediction, it will grab the next frame and start trying to classify that. While it's happening, we might put the video image on the screen as well so that we can see what we're seeing. You can see what I'm seeing, and it will put the prediction up as text, just like we did before. So I'll press go, allow my webcam to be used, and we'll see if this, well, is it going to work? Eventually it will work, I'm sure. Maybe I'll start it again. Oh, it worked just at the last minute, sorry. You'll see behind the curtain here because you can see my green screen and me. Oh, here we go. I apparently am a mask. You can see my lovely vent up in the ceiling. Ah, yes, venti. Let's see if we can get it to classify something. Is that mouse, computer mouse? Doesn't seem right. What about this one? Drumstick. Lipstick. Lipstick it's similar to lipstick, but it's not. Fountain pen. It had some kind of pen. Pen. This, in fact, is a pen, so that's close enough. I'm going to call that a win. What about this? It thinks everything is a pool table because of the green screen, so that's a shame. I'm trying to make it think this really big. CRT screen, no. Okay, that's not working. What about this one? Really is confused about things being green, being a billiard table because of the green background. Could be a projector or a vacuum cleaner, apparently. Beer bottle. This is not a beer bottle, it's a water bottle, but that's close. Phone? Cellular telephone. It knows what that is. That works well. What else have I got around here that we can show? A book. Christmas stocking. It's confused about books. No, it doesn't know what that is. What about this? Cellular phone. joystick. That's really wrong, isn't it? Oh well. So the video is more fun. It does seem to think that I'm a punching bag sometimes, or a mask, which is concerning. I'm not a mask. I am a man. I'm just going to stop that because it's weird. I'll go back to my lecture for a minute. So we've learned that this is fun to play with. We've learned that it gets things wrong all the time. We've learned that we can use machine learning to make predictions about things. If they're not correct predictions, are they very useful? I suppose we could make some art to find out. But I did have that question before about problematic things. So what could possibly be problematic about figuring out if something's a doggo or not? That's my question for the day. What could be problematic about that? Well, the problem is not in the doggo. The problem is where the data came from to create the machine learning system. I know that where this doggo came from because I found that image on Unsplash, and Unsplash has its permissive license, and as you know, it's sort of one of the places that I let you take inspiration from in this course. But I don't know what went into the MobileNet model. That one I just loaded up from ML5. So who knows what data was used to train that? Who knows whether it works or not? I really don't have any easy insights. I did do a bit of digging to work out exactly what was going on there. So we don't know what MobileNet is. It's just provided to us. It's just this pre-configured algorithm. So the question is what the training data was and what was expected from this system. So the training data actually for MobileNet was a subset of a data set called ImageNet. And there's some of the labels coming up here. And you can find out about ImageNet by clicking that link, but it's a data set which has been around for about a decade now, used for competitions, training image classification system in a competitive way to make them get better and better over time. And it's become used in a lot of image classification systems, not used for competitions, but applied in real world applications. And it's trained using a lot of images that have just been found on the internet. So you can see a lot of the examples coming up now. The question is whether the MobileNet implementation that we've got present in ML5 is actually doing its job. And I guess I would argue that it's not really. When I had one image, I think, in all the ones I was showing you where it really knew what it was. It really knew it was a Labrador. And that image was probably in the data set because I found that image on Google, just trying to find the most dogly image I could think of, and a very typical image of a dog. Probably it was included in the training data, and so of course it seems to get that one right because it's been trained to get that one right. But when it sees an unusual dog that it hasn't seen wearing a pink jumper, it thinks it's a fountain. So obviously the MobileNet system, that particular machine learning model is designed to work well with phones or in web browsers, designed to be fast and work in a low power computing expectation environment, which is great, but obviously it's not working perfectly. We can improve this though. We can improve this. I'll show you how in a minute. Another thing to be concerned about when thinking about machine learning systems is that creating a machine learning algorithm and running one can sometimes be extremely energy intensive, and there are potentially hidden costs in creating new machine learning systems. And sometimes those costs are borne by very large tech companies who are prepared to invest big money in training machine learning algorithms, but we should question whether it's worth it to train those algorithms. What are we actually getting out of it? What is the impact on these algorithms in terms of not just how well they work, but the cost of training in terms of energy and potential carbon emissions? And these questions are answered by some people who provide ways to compute the potential carbon emissions from different machine learning projects. So there's folks who are working on ways to maybe understand these hidden costs and include them in part of our consideration of value in machine learning systems. So let's try to make MobileNet better. How are we going to make MobileNet better? Well, so far we've been just using a pre-trained model, but now we can actually improve this by making our own custom model. So we're going to do a little bit of training as well as inference. So there's a website called Teachable Machine, which lets us tune a mobile net algorithm to work well with the specific images that we want to show it. So this is where things get interesting for our artworks, because we might be able to use Teachable Machine to have different images, different things that I've got on my desk, and we can make sure that it gets the right answer. So I'm going to go to my other laptop. We'll load up Teachable Machine, and we'll get this party started. Where's Teachable Machine? There it is. Yeah, train a computer to recognize my own images. Get started. We're going to do this right now. Hopefully it works. I want an image project. There's lots of options. So you've got a movement project, the pose one, that's really cool. Audio projects, and the image projects, the standard image model. So we're going to have a few things. I think I want to recognize my coffee cup, this nice colorful one. I want to recognize my whiteboard marker, and I would like to recognize my multimeter, because this is not a phone, this is a multimeter. So these are the things on my desk I'm going to add. Going to be cup. I might add my water bottle as well. Class 2 is going to be pen. Add a class. Multimeter. Add a class. Water bottle. I'll just say bottle. And add a class just for me, Charles, because I'm here too. I don't want a capital C. Okay, now here's the trick. We have to get some data, and we will know where the data comes from for this part of the machine learning training, because I'm going to record it with my webcam. So I'll get myself run the frame. This is the cup. Actually, I don't want to be in the frame for this one. I want the cup to be in the frame. I'm just going to hold the cup, and we've got a bunch of cup data, 48 images. And now I'm going to do the pen over here. Okay, got some images. The multimeter. Cool, and my water bottle. Okay, great, and then just me. Woo! A few more. Okay, now we've got all my training data. I can hit train model, and it goes and thinks for a while. I hope it's going to work. How about I get content flagged for this? Almost there, 40 out of 50. 49 out of 50, cool, okay. So, now we can test it. I'm just going to move myself. Uh-oh. Don't want to move that, I want to move myself over here so you can see what's going on. Maybe I'll move myself over here. You can see a bit of the edge of my green screen, sorry about that. Let's try things. Charles, that seems to be working. Here's pen. If there's nothing there, what do we get? Oh, I should have just had nothing. Oh well. Pen, that seems good. Cup, seems to be working. Multimeter, seems to be working. What about this one? Bottle. We did it. We've got a working system. How are we going to use this? How are we going to use this in P5? That's the trick. Now there's a little thing I have to be careful to make sure I get it right here. I want to upload a shareable link, because I'm just going to load it straight. I'm going to load it straight into P5. I've already got my P5 sketch. organized. Uploading. I can also, I might download it as well, just so I've got it stored away. But nice to have it up on in the cloud. Okay, I got my shareable link here. And then P5JS gives you little instructions about where to load your model. So there's my model. Here's my code, or I can just copy the URL. I'm also going to download it. But I've got my shareable link there, copy that URL, and then I'm going to go into my pre-made one I prepared earlier. Teachable machine, Charles model. Okay. Get a new one, whoops. I make a new one every year. Okay, this is the 2022 model. Okay, now that I've got my, move my face over to the other side, I've got my model listed there, and then the rest of the code is very similar to what we were doing before. I've got a preload, loading up a classifier. I've got a video, create capture video. It's flipping this so that it's kind of a mirrored video and classifying with the same idea. Classify video, taking an image, flip video, got results. Very, very much the same concept as the previous example. Let's see if it works. I'll use the camera. This one's a bit of a, well, the demo is not so good. Oh, what? That went away. I finally got it to work. I'll close that one off. Leave page. Charles model. I'll let it load this time instead of racing ahead. How about that? Here we are, Charles. So I've got the Charles classifier working correctly. What about the cup? Cup. Nothing turns into a pen, which is not quite right. Here, pen turns into a pen as well. I really should have classified nothing. Otherwise, that's a rookie error with your machine learning systems. Covering all the bases in terms of classification. I've got my multimeter working perfectly. It's pretty responsive, isn't it? Works well. What else did I have? My bottle. Yeah, knows about the bottle. If I'm in front of the bottle, I can pretend to be a bottle. If I move it that way, it goes Charles. Charles, bottle, Charles. Pen. Pen, pen, apple, pen. Cup, pretending to be a cup. So we finally have a machine learning system that works. The moral of this story is that if you want your thing to work, you have to train it yourself. That's a classic moral in machine learning, because you know where your data comes from when you're training it yourself. This one, actually, it does rely on an existing trained mobile net, trained on a lot of data from the internet, but it adds an extra couple of layers that are trained quickly in your web browser. So it's doing what you could call transfer learning, or just tuning the model as a last step, not having to train the whole thing. So I can stop that one now. And in fact, I can go back to my other screen, because I don't need the other laptop anymore. So we've done artisanal bespoke machine learning. Now we're going to have a look at a couple of other fun examples. A completely different kind of machine learning model is this one called SketchRNN. And the idea of SketchRNN is to be a model of how someone would draw a picture in X and Y coordinates. So the model generates a drawing by moving an imaginary pen around the screen. Really fun model to try out. Let's load it up. I've got an example of it working. machine learning. I think Dan Schiffman has a nice model as well, a nice example of this as well. There's a little bit of detail in getting this to work because each of the predictions, the prediction isn't a whole picture. The prediction is a movement of the pen. So you have to, just as if you were moving your mouse across the screen, you have to draw a stroked path as that pen is moving. Draw a line for each little draw step. So we can just try this and see how it goes. I think it's set to the cat. It just should start drawing cats when it loads. Oop, it gets them low. Get some cats. There's one. There's another cat. And this machine learning system was trained on some data that Google collected from people who were playing a little game. So they were doing a sketching game where they had to quickly draw a thing, and that they used that game to collect a lot of sketches of different kinds of objects and train this machine learning system. There's a cat. Cat. Okay, so we can see cats seem to be working. We can see what other options are available. There's all of these different models. So we could have an alarm clock. That's the very first one. Try that instead. There's a big alarm clock, isn't it? Oh, there's another one. Let's clear those again. So this one's got the bells. They sort of look like Mickey Mouse clocks, don't they? This sketch is not making very creative use of these, but there could be some way to use this model in creative uses. I created a similar system to SketchRNN for working with music, for modeling how people would move their finger on a touch screen to create music, and play with that for a long time. Yeah, SketchRNN. We'll try one more model. What are we going to do? How about the Mona Lisa? It's got the hair going, got a lot of frame work and a lot of hair work going on in Mona Lisa. Well, there's just the person. There's a frame. Yeah, wow. Okay, well, we're making art, aren't we? Art within art within art. So that's SketchRNN, really fun system. This is how it works, the little demo. You can click here to see the example. And the prediction here is an object with X, Y, and pen states. So the X and Y are the amount that the pen should be moving in an X direction and a Y direction. And the pen state is whether the pen is up or down. If it's not up, you can't make gaps. You need to have spaces in your drawing. So you lift your pen up as you're drawing to start the next shape. So that's why the pen state is there. There are lots more ML5JS models. We're not going to go through any more. There are lots of fun ones to do with image classification and processing. So if you want to use a webcam and get it to do something interesting, you could be using an ML5 model to do some interaction with the webcam. There are sound recognition models and text generation models, which are also super fun. I would suggest you have a look at all of those and see what you find if you're interested in machine learning and creative arts. Now we get to the final chapter of this lecture and the final chapter of the course. A few examples of machine learning art, machine learning systems creating art in P5. Not in P5, sorry. These are machine learning used in real art practices, not just in P5. Sorry, that was a tick. I'm just obsessed with P5. So here's an example. Alison Parrish is a wonderful poet and experimenter with using machine learning models with text. And one of Alison's pieces is this work called Compasses. So the idea of compasses was to create a machine learning model that would invent new words. So Alison was interested in how how you might find words in between other words. So there's machine learning models which sometimes are used to find the images between one image and another image, infill those spaces in between, and you can apply this same idea to words, and then create these kind of visual poems with 4 words that are real: phlegmatic, sanguine, choleric, and melancholic, and then words that are in between on each side, predicted by this machine learning model. So there's a few links to different examples, but the words in between, shag-knitting, Calione, chalentic, phalantic, calatic, are invented by this system to be in between those concepts. This is a wild one. Databots are a kind of band or project or something who create infinite machine learning generated music. So I'm not sure if I'm going to get my desktop audio here. Probably be a bit wild if I started playing that, but we'll get something. Oh, is it working? Am I getting audio? XUSB. Oh, my speakers are turned down, that's why. Turn them up. So this is some infinite death metal from Databots. And they've got a couple of different YouTube channels showing infinite different kinds of music. It's kind of authentic, isn't it? So, yeah. So Databots have these projects where they just have systems that are just generating music continually. So they've got their model already trained, and they're generating music continually and streaming it on YouTube as a continual service to the world to see. Relentless. I'm the only one watching, so not everyone is happening here. This just creates technical death metal via live stream, 24/7 to infinity. Wild project. So that's Relentless Doppelganger Databots. You can have a look at some other Databots work if you're interested in the weird and wonderful stuff they do with music and machine learning. Here's a cool piece. This is an interactive work by Mimo Atkin, really interesting interactive media artist, called Learning to See. So one of the things people do with machine learning models is generate images, and the idea with this model is, just want to move my mouse here. The idea with this model is to generate images continually based on what is being seen by the computer here. So you can see the computer is seeing this pile of objects on a table, and then it's creating an image of waves that's sort of in the same shape, isn't it? So the idea with this system is to let people construct some image in front of a webcam and have this computer continually trying to update the learned image. And it's just continually trying to improve these images all the time, learning to see. So it's learning in front of you. And a super interesting way of using AI to let someone interact with a computer system and create something in a small generative way. So a really cool idea for a installed artwork. You can have a look at a video there. I think there's videos through this link of these works in progress. Dilpreet Singh, Art or Not app. So Dilpreet Singh is an Australian artist who is working in a lab at Monash called Sensi Lab, and one of their work was this idea of training a simple image classifier, just like we've been doing in this class. And the concept with their image classifier was to classify whether an image that the phone could see was art or not art. So it was an art classifier, art or not. Kind of a silly concept, really, because it's playing on the idea that art is something which can easily be identified, but maybe at least we can ask our question on how much it can easily be identified from just the look of an image, and how much we need to know more about the context to decide if something's art. So Dilpreet trained this model with images that were definitely art and images that were definitely not art to tell whether something was art or not. and could tell you whether something's come from different places online as well. So you could go around with this phone app and take pictures of things, and it would helpfully instruct you on whether it was art or not. Another concept here. This is some work that I've been collaborating on with PhD student Benedicta Wallace. And Benedicta has been interested in creating or generating human motions using machine learning. So Benedicta's work has involved collecting a lot of data from dancers and using that data to train machine learning models that could generate dances in different ways. You can see lots of cool videos from Benedicta through her papers and on her videos. And one of the outcomes in this is now working with dancers to work out how these dance generation systems could be feed back into a practice. Can a dancer work with this system to get new ideas or create dances that reflects the mistakes and weirdnesses of the AI-generated ones as well? So a really cool project and a great idea of how you can collect data to create your own machine learning systems. Unfortunately, the dance data collection part was very time consuming in this project, so it's certainly something you have to really work at to get a cool outcome. Bit of further reading and a bit of further watching. Artificial intelligence art, AI art tools, AI art paintings in Australia. If you're interested in this stuff, there's a lot of videos by Dan Schiffman looking at the specific models within ML5JS. He's done a lot of deep work on implementing all of those and showing how to use them in P5. So you could have a look at those to see how you could integrate this stuff into an artwork. And with that, folks, we've made it. We're at the end of COMP1720. For the folks who are streaming online, thank you for coming on this journey with me. We've had a small but committed group of folks every week live online in the lecture interacting. It's certainly a big journey to go on through 12 weeks, turning you folks into interactive computer artists. If you want to do some more creative coding with me, I run another course called Sound and Music Computing, which is running in semester 1, 2023. Sound and Music Computing. So you can come and look at this one. It's COMP4350. So this is a course for the later year students in the audience. We also have a master's course called COMP8350. If you've a master's student and you've done 6720, which you will have done if you're watching this lecture, then you're welcome to join Sound and Music Computing next semester if you want to do some more art making, except with a total sound and music focus. So in this course we make interactive artworks that might hang on a wall, and in Sound and Music Computing we create new kinds of musical instruments and musical performances with our computers. So similar ideas, but a different focus, a different medium, and some different technical problems that have to be faced in the world of sound and music computing. But if you're interested in learning about how synthesis works, how you can create music with computers from scratch, how you can create music with a programming language, how you can create a new kind of synthesizer, a new kind of interface for making music, maybe Sound and Music Computing is the course for you. Also, if you're a CS student, think about how you could apply what you're learning in this course in a project. A lot of CS students, or most CS students, do different kinds of projects throughout their degree. I'm not actually offering any further projects in 2023, but if you're in first year and you're thinking about doing an honours project in 2024 or beyond, happy to give me a call sometime or drop me an email or reach out on Teams. Always happy to talk to folks about projects. And with that, I think we can wrap it up, folks. I'm happy to answer further questions about major projects on the forum, on the team. I'm looking forward to seeing what everyone's got. We'll make sure that our major project showcase website is looking spick and span for the first day. We'll get it all cleaned up. Make sure you got your thumbnail.png uploaded so that we get a great website. Everything looks good, and you'll be able to check out everyone else's major project with our online gallery at the end of the course. And with that, I will let you go. Folks, I'll see you around the place. Ask me a question on the forum. Hope to see some folks in sound and music computing next year. Catch you later.